second important operator is the divergence operator. As I have introduced the contraction product, the divergence is the contracted form of the gradient. So if I ask you to compute the divergence of something, you have to first compute the gradient of that quantity and then perform the contraction product. For example, I want you to compute the divergence of, again, that vector field, for example, velocity. You have to compute the gradient operator first. You ignore this dot product here. This is the gradient of velocity. Compute this. I've already computed here. Then apply the contracted product. And as I told you, the contraction is the trace of the contraction process produces the trace of that matrix. So the contraction of the velocity gradient tensor or matrix, or the dot product of the del operator with the velocity, is the trace of this matrix. The trace of this matrix is the sum of partial derivatives of three components of velocities with respect to three coordinates. The trace of the velocity gradient tensor, which is equal to that quantity. This is the divergence operator. Pay attention that, again, similar to what I have written here, the del operator is a vector. Again, this is a vector. 1 plus 1 is 2. When you perform a contracted product, the result will be a scalar. So this is a scalar. In contrary to the gradient operator, which always increases the order of its input, the divergence operator always decreases the order of its input. So the divergence of a vector is a scalar, the divergence of a matrix is a vector. For example, the divergence of the stress tensor, which is a matrix, is the force vector, which is a vector. And the divergence of the heat flux vector is again a scalar. Divergence of velocity is a scalar. And also pay attention that that's the minimum order of input of the divergence operator is 1. So we don't have the divergence of a scalar. It's meaningless because we have to perform the contraction process. So, and we don't have a negative order for a quantity. So the minimum result is 0, order of result is 0. So the sum of orders of these quantities will be at least 2. So this is a vector, and this at least has to be a vector quantity. So we can compute divergence of a vector or divergence of a tensor or a matrix, but it's impossible to compute the divergence of a scalar. From the physical viewpoint, the divergence shows or represents the net flux of something. For example, when I talk about the divergence of velocity, it means that I want to compute the net flux of mass in that point. So if the velocity is divergence free, or the divergence of velocity is 0, it means that we don't have the net flux of mass in that point. We don't have sources or anything seems, and the density is constant, or the flow is incompressible. Or the divergence of heat flux vector shows the net input heat into that element. Or the divergence of stress tensor represents the net exerted force on that element, which is used in the conservation of momentum. This one is used in the conservation of energy, and this one is used in the conservation of mass. When you want to compute the divergence of a tensor, or generally when you want to compute the dot product or the contracted product of a vector and a tensor, you have to compute the dot product of the vector to the first row of the tensor, the dot product of the vector to the second row of the tensor, and similarly for the third row. Here we want to compute the divergence of a tensor, so the first vector is the del operator. So the divergence of a tensor is a vector with three components. The first component is the divergence of the first row of the tensor, and similarly for two other components, I have written the results. The result of the dot product here. You can see we have three components.